Hey, welcome back. Today we're going to be talking about what is a limit and what exactly is it used for. So let's jump straight into this. We're going to have this graph f of x in the xy plane. And f of x is going to, let's call it x cubed. So f of x equals x cubed. And it'll look something like that. And so now what we can say, as I'm sure all of you are aware, is we could say f of, let's say 1, or let's say 2. F of 2, we'll say it's right there. So this is f of 2, and we're going to say that that equals 8. Because, right, 2 cubed is 8. So this is all well and good. This is what we're all used to. But now what if we say, instead of evaluating f at 2, we say the limit as x approaches 2 of the function f of x. What is this going to equal? Well, because f of x is continuous, that means that if we put our pencil down on the paper here, we wouldn't have to pick it up the whole time. My pencil's acting up. We wouldn't have to pick it up the whole time we trace the graph. And so what this means is at any point on the graph, if we take the value of f of x, so f of 2, which is 8, if we take that value, it's going to equal the limit at that point. So this would also equal 8. But so that still doesn't really answer our question. What is a limit? What does this mean? Well, so we have this thing down here, right? So x is approaching 2. So what does it mean for x to approach 2? What we're saying is as we, so this is our x-axis. So as x gets closer and closer to 2 from each side, so we may have 2.1 and then 2.11 and then 2.11, or sorry, hold on, whoa, that's not right. 2.1, 2.01, 2.001, right? So we're getting closer and closer to 2. From this side we might have 1.9 and then 1.99 and then 1.999. So we're getting closer and closer to 2. What does the function approach? Another way we could write this, instead of just writing these numbers on the number line, is we could write it like this. So we have f of 1.9, f of 1.99, f of 1.999. And then, of course, we have f of 2, which is 8. Then we have f of 2.001, right? And then as we get farther away, it's going to be like this. And so what we're saying is, as let's say we didn't know what f of 2 was. Let's say we just don't know it at all. I'll still write it there, but we have no idea what this could be. We're saying that as we evaluate these numbers in this direction and these numbers in this direction, as we get closer and closer to 2, what does that value approach? So let's get this up on the graph. Let's say f of x, we'll use 2 hands to type so it's faster, equals x cubed. And now we can say, we can start plugging in. So f of 1.9, f of 1.99, f of 1.999. And so we have these values, right? So we have 6.8, 7.8, 7.9, and so we're getting closer and closer to 8. We're getting closer and closer to 8. And what if we go to the other side? So now let's try, of course f of 2 is going to be 8. We can try f of 2.1, f of 2.11, f of, oh sorry, I keep doing this, 01, 2.001. So it also is getting closer to 8 from the other side. So we can even plot this point here. So here's the point we're talking about. So all we're really saying is as x gets closer to 2, right? So you see we're at 1.8, 1.9, we're getting closer and closer and closer and closer. That y value is getting closer and closer to 8 until it eventually hits it. And this is true from both directions. So basically, limits for a graph like this, continuous graph, are easy, right? Because since the graph is continuous, it's just going to keep approaching the same value from both directions. So really the limit, or this is actually how we'd write this, and this is actually kind of important if you can understand this. But so for this function of x, which is continuous, and we're going to blow this up actually because this is important. So for this function of x, which is continuous, the limit of f of x equals, oh, that's not what I want to do, equals f of a. So, okay, so sorry. So the limit as x is approaching some value a. For this continuous, remember this is continuous, that's important. For this continuous function, as x is approaching some value a, the limit is going to equal the function at that point. So what we're saying is for any given value f of a, this is f of a, because this function is continuous, the limit as x approaches a, right, so as x is getting, if this is a, as x is getting closer to a from both sides, this limit is the same as the actual value here, okay, because it's continuous. So why don't we do this? Let's get this new graph. And let's call it x squared minus 1. And we will make it g of x, and we'll make it orange. So it's going to look something like this. And this is 1, and this is 1, or negative 1, this is negative 1. So what's going on here is the same thing, right? This graph is continuous. For any of these points, let's practice actually. So let's say limit as x approaches 1, limit as x approaches 0, limit as x approaches negative 1, limit as x approaches 2. So this is 2. So what are these going to be? And this is all of g of x. I know I inverted those colors, but hopefully it still makes sense. So take a moment, try to think these through. It's not all that challenging, especially given what we just went over. But so if you're thinking as x approaches 1, the graph is approaching 0, right? So this is 0 on the y-axis. So as x gets closer to 1 from the right, as x gets closer to 1 from the left, the graph approaches 0, right? I know that's a lot of arrows, but hopefully it makes sense. Same goes for negative 1 over here, right? If you plug in g of negative 1, you're going to get 0. The graph is continuous, so that means that the limit also equals 0 there. Now down here, it's looking like we're approaching negative 1, right? Here's negative 1. So this is negative 1. And then, oh, I don't want those arrows. Negative 1. And then as we approach 2, I know I didn't draw the whole graph here, but g of 2 is 3. So that means the limit as x approaches 2 is also going to be 3. Okay, so that was pretty easy. Now, we're going to go over one final example in this video. Oh, there we go. And this is where, because you may be saying, okay, well, kind of what's the point in a limit? I feel like we can just, we may as well just evaluate the function instead of taking a limit. Like, why do we even have these limits? But the problem, and this is going to be something we talk about again in a future topic much more, but the problem is that sometimes you may have some function, let's call it h of x. And let's say h of x is x minus 2 times x over x minus 2. And so one may say, okay, well, how are we going to graph this thing? Well, x minus 2 over x minus 2 is 1. So like we may as well ignore this, right? And this is just h of x equals x. And there's our graph. But there's a problem, because we can't just ignore that when we graph it. Because what happens, right, so an observant person may say, well, if you plug in x of 2, you're going to have 2 minus 2, that's 0, over 2 minus 2, that's also 0. So now we have 0 over 0, that's undefined. So h of 2 is undefined. There is no value for h of 2. So now how do we graph this? Well, what we do is at 2, we're going to add something called a hole. And so a hole basically just means there's a part on this graph that is just completely undefined. But despite that, the rest of our graph is defined. Everything even infinitely close to that point. So h of 2.00000001, that's defined. H of 1.99999999999, that's also defined. The only thing that isn't is h of 2. So you may see where we're going with this. While we may not be able to define h of 2, doesn't equal anything, we can still define the limit as x approaches 2 of h of x. So what we're saying here, right, because you may expect h of 2 to equal 2, right? That's where the graph approaches. Think about what we mean when we say that's where the graph approaches. From the left side here, from the right side here, we're approaching this point as x is approaching 2. So therefore this limit is evaluated as 2. And so that's going to probably wrap it up for today. It's a good overview of limits. In the future, we'll go into more depth about these discontinuities, and we'll start to see how these limits can be used to solve more complicated problems.